Hello, this is a mini lecture for chapter 2.3. And again, this is a very short chapter, so it's only one lecture, but it's very important information. So far in the class, you probably feel overwhelmed by different things we study. One day we studied echelon form, the second linear system, the third one we're going to transformation. So all of this information feels probably disconnected to you. The invertible matrix theorem ties all of these properties together. So basically this theorem is tell us that there is a lot of properties which we discover which can be right for the n by n square matrix. And the invertible matrix theorem give us the list of like laundry list of things which leads from one to another. For example, if A is invertible matrix, it is a row equivalent to the n by n identity matrix. And by the way, every single statement in invertible matrix theorem is two-dimensional. All of them can be either true or false. So for example, if we have a matrix A row equivalent to n by n identity matrix, it's guaranteed for matrix A to be invertible. Also, if matrix A has n pivot positions, again, we can say that it's invertible and both A and B is true. And also matrix A, if any of the A to C properties true, it should, then the homogeneous equations written for our matrix A has only the trivial solution. Also, the column of our matrix will form a linearly independent set. Okay, you see how we're tying together so many definitions we learned. Also, the linear transformation formed by our matrix would be a 1-to-1. Also, the non-homogeneous equations formed by any right-hand side B will have at least one solution for each value of B in n-dimensional space. Also, the columns of n will have a span of n dimension, the size of our square matrix. Also, the linear transformation from X to AX will map n-dimensional space into n-dimensional space. Also, there should be a matrix C such that matrix C multiplied by our matrix A will give us an identity matrix. And you probably recognize it as just basic definition for invertible matrix. But we know for our invertible matrix that we can switch the matrix in the multiplications and we still get an identity matrix. So we can say there is an n by n matrix D such that matrix A multiplied by D still give us an identity matrix. Finally, our transpose matrix A is an invertible matrix. So basically, if you find one of this statement that's true, you can infer any other. Or or if one of the statement is not true, the rest of them are not true either. For example, if you find that the columns of A span n, you can conclude the 10 other statements on the spot. You know that the matrix is invertible. You know that he has an n pivot position, and so on and so forth. Okay, so let's just see how would you work with using invertible matrix theorem in a practical application. For example, we have a matrix A, and let's just try to figure out if it's an invertible matrix. Any statements from B to L can be appropriate. We can go to test any of them. I personally try to find the easiest way to do things. So let's see. Which one is the easiest, takes the least calculations? I would go for C. So the A has n pivot positions. It's easy to reduce matrix to echelon form and just calculate how many pivot positions do they have. Okay, let's perform the row operations, and we usually start from the first column, and we need the two bottom positions equal 0, so we perform the row operation and write the equivalent matrix. And then we need to get rid of this -1 to the second column to get the pivot position for the second column. So finally, look at that. We have 3 pivot column with 3 pivot positions. So indeed, we have 3 pivot positions for the 3-dimensional matrix A. So we can refer to the property C in invertible matrix theorem and say that indeed, because we have 3 pivot positions, our 3-dimensional matrix A is an invertible one. Okay, so now I would like you to go to the end of the chapter 2.3 and start working and practicing with some exercises.